Hi, everybody. Today we are going to talk about global positioning system. For ES 2070 engineering surveying, this is covered in chapter 15 of your textbook. And in ES 2670 practical surveying, this is covered roughly in chapter 3 of your textbook. So we're going to cover this today because at some point during the semester, we will have a guest surveyor come in, and he will give us a demonstration using a GPS unit. GPS receivers of survey quality are very expensive, and Northwest College does not own one. So Engineering Associates has been very good to our school and has always provided a surveyor and the equipment to come out and to do a course for us during the course of the semester. So I've talked with the surveyor, Zane Logan, and I'm not really sure when he's going to come. So I want to do this lecture and have the homework done in advance of his presentation, whenever that might be, so that you will be knowledgeable of the subject. So we're going to talk about the principles of global positioning system and the applications. The first thing is the global positioning system is a series of satellites. Right now it's about 24 satellites that are in an orbit 20,000 kilometers above the Earth. And this is originally the United States Global Positioning System, or NavStar, was originally put in place as a military set of satellites. So it's been around for a long time. There were fewer satellites in the original system, and more have been added. Another thing that's really increased our ability to use GPS for non-military reasons is that back, oh golly, a long time ago during Bill Clinton's administration, there previously was a protocol called selective visibility on the satellites, or selective availability. And what would happen is that satellites would just sort of randomly, or in a pattern of some sort that I'm not aware what the nature of the pattern was, would be turned off so that you could not receive a signal from them. And this was done primarily as a defense mechanism to make sure that we did not have people who were triangulating the position of the satellites and then sending missiles and taking them down or whatever. But anyway, during Clinton's administration, selective availability was turned off, and so now they're all available all the time. And what that's really done for using GPS is it's allowed us to use GPS pretty much 100% of the time. It's been years since I've seen anywhere or any time when you didn't have enough satellites available in order to do a good survey. The only time the GPS really gets interfered with is if there's a lot of like tree cover, because you have to have a clear line of sight with the satellites that are visible in the sky, meaning above the horizon. So sometimes if you're in a very narrow valley, or if you're in a heavily wooded area, you may not be able to use GPS. So the historical development, the launch of the first GPS satellite was in 1978. Kinematic GPS surveying became available in 1985. It really didn't have anything to do with the satellite system. It had to do more with the computer processors that the GPS receiving units were capable of carrying on board. 1985, of course, was a really, really long time ago. But prior to that, it was just very difficult to take a lot of intense data and process it into something meaningful in terms of distances. So kinematic surveying was not available until then. Now, what we use right now is called RTK, or real-time kinematic, which means you get the reading, your receiver gets readings from the satellites, and we instantly have the data as to location, elevation, XYZ plane coordinates, XYZ coordinates, so XY plane, Z elevation coordinates. And the data comes to us and is processed not really instantaneously, but very close to being instantaneously. So they just go through some things like that. So we started with kinematic, then we came up with the RTK, real-time kinematic, and in 1993, and continue on selective availability was set to 0 in 2000, which, as I said, was in the Bill Clinton administration. So those were some of the landmarks in GPS. So GPS is a marriage between the receiving units that we as surveyors use, or engineers or private individuals who have enough money to buy a GPS system, and the set network of satellites above the Earth. There are other systems besides the Navstar that are put up by different organizations, different governmental organizations, or there may be some private satellites as well. I'm not certain about that. But anyway, you have to have a certain number of them available or visible to you in the sky. And visible, of course, you can't see them with the naked eye, but where the signal is above the horizon and that you can receive it with your unit. Now, survey quality GPS is quite a bit more expensive than like personal handheld GPS units. You may at some point in your life have used like a Garmin, or if you use a navigator in your vehicle, all of that is GPS, but it's not to the 100th of a foot GPS. The processor that and the system that allows you to get to survey quality data is quite a bit more expensive. The satellite data is the same, but what your receiver can do with it varies greatly depending on the quality of your receiver. So the system overview: the total GPS configuration is comprised of 3 different segments: the space segment, which are the satellites orbiting around the Earth; the control segment, which are the stations positioned on Earth's equator to control the satellites; and the user segment, and that would be whatever you're using, whether it's a Garmin or whether it's a Trimble survey quality GPS system. Now, there's another thing too. If you do have a Garmin or a handheld GPS unit for hunting, there's a system called WAS, and what WAS is a series of land buoys that act as a second leg of a triangulation unit. So the buoys are put in place by the company, and then you not only triangulate from the satellite, but you triangulate from that land buoy or a series of land buoys as well. And that allows you to really close in on the data to a pretty high degree of accuracy. So they're much more accurate than just a handheld, which may be only accurate to within a few meters, maybe 10 feet. So you can close in if you have a WAS system. And of course, survey quality has the best data capabilities, the RTK, and the very, very high degree of accuracy. But once again, it's the same signal off the satellite. So the basic principles of GPS: resection for unknowns, calculating the distance to the satellite, and calculating time. Now, it's sort of an interesting thing, but when we're talking about signals from satellites, basically they're traveling at the speed of light. And there's no way that the signals can be reduced to a distance using distances equal to rate times time, because the time element is so fast. So there has to be a reduction of the data, or a series of signals, or a series of variables that's reduced in basically an array of overspecified equations. And because of that, what we're really dealing with GPS is at least 4 satellites to get X, Y, Z, and time. Sometimes you need more. And it sort of depends on the position of the satellites compared to the position of the receiver. But like if everything's straight over your head, you don't have a good spread, and you can't get a lot of distinction between elevations. So you may need more than 4 data points, but you need at least 4 data points in order to calculate 4 variables. It's just basic principle of algebra: 4 equations, 4 unknowns. So X, Y, Z, time, 4 variables. It's also really interesting because in GPS, the satellites are moving at a different rate than the Earth, and the relative velocities of them are different enough that we have to calculate for the relativity effect of time dilation. which is really interesting because as far as I know, it's the only technology on Earth that requires a correction for relativity. And I may be incorrect about that, but I'm going to go out and say it's at least the first major technology that requires relativity time corrections. So there are things that can affect the accuracy and precision of global positioning system. We have the ionospheric and atmospheric delays, which are just reductions in the speed of the signals. Satellite and receiver clock errors, which are need to be compensated for pretty continuously. It's done automatically usually. When I say usually, I mean I've never seen it not done automatically. Dilution of precision, the multipath issues, which we'll talk about a little bit later, and blenders. So GPS is very accurate and very precise. However, there are some factors that we need to understand in order to use it appropriately and to not assume that we're getting an accuracy or precision that we are not getting at that time. All right, so here are just some examples. We have an example of a block signal where you might think that you are, maybe you're down here somewhere and you think that you are getting a straight signal, but really you're getting something that's bouncing off of a billing. Multipath is where you have more than one type of thing. So you have the satellite thinking it's talking here and thinking it's talking here. See that you end up at nearly the same point, but that the path here is very, very different. And then the corrected signal. It tries to compensate for all of those things, but some of the things it just can't understand what the data means as it's coming in. So factors affecting accuracy. Remember, there's a difference between accuracy and precision, because if you recall from chapter 2, especially engineering surveyors, accuracy has to do with how close you are to correct. Precision, it has to do with how close the measurements are to each other. So basically factors affecting accuracy then can be the number of visible satellites. Once again, you need at least 4, but the constellation or the shape, the relative position of those satellites to each other also makes a difference. So if you have 4 that are well spread out, they're not in the same line, they're not very close to each other, you can get a much better accuracy than if they're all in a line, or if they're all very close to the horizon, or if they're directly above head. Position, dilution, and precision, satellite elevation, multipath, and the distance between space station and roving receivers. Once again, they're all sort of the same ideas. So you have a satellite that broadcasts GPS signal, you have some sort of a receiver, and this would be like one of the stations that we were talking about in terms of a land station to tighten the signal, I guess would be the best. Tighten the calculation is the best way I can phrase that. And so the signal is corrected and broadcast back, but everything has to agree. Time factors have to agree. Location factors have to agree. Everything's checked. And sometimes GPS will just tell you it doesn't understand what's going on. Not very often. You can move a little bit or wait a couple minutes, and usually that will clear itself up. Okay, so next thing we're going to talk about are the advantages and limitations and a little bit about the different uses of GPS technology. Obviously, GPS is very effective for surveying, but there's lots of other uses for the technology as well. The signals are all coming off, there are different signals that come off of satellites, different bands of signals, and some of them are used for different types of communication, with GPS being one of the types of communication. So what do we use GPS for? For location, for navigation, for tracking, for mapping, and for timing. So tracking is really interesting. For example, if you are a parent, you can put a little tracker on your kid's phone and you'll always kind of know where they are. Don't know, I mean, it might come in handy in some instances, but there's some ethical issues involved in that as well. There were some issues involved in, I think it was running shoes that had a little GPS receiver, and people were using it to time their runs and to get very precise, like a pedometer reading really, but it turned out that they were trackable. So if somebody was on a cross-country run, it was possible for some person who shouldn't know where they are to be able to find them based on that signal. So there's some ethical issues involved in that. But in terms of technology, it's quite effective. So competitors for GPS, GLONASS and Galileo. We talked about the Navstar system as being a United States system. GLONASS is a Russian system. Galileo is the European Union and the European Space Agency. They all function similarly to each other. I do not know if they are totally compatible. So that remains to be seen. All right, so like we were talking about, we have GPS has 3 different types of data in the signal. We have a pseudo-random code, the ephemeris data, and the almanac data. These are things to establish where it is and when it is. So ephemeris data, ephemeris can be published manuals, but of course we're talking about digital ephemeri data at this point, similar with almanac. So those are just databases that GPS systems or the reduction, the computational portion of the receiver unit has access to. And so it's always checking, your receiver is always checking with the satellite to make sure that everything corresponds. In the old days, I don't know if they still do this, but when you would have handheld Garmins, sometimes they would ask you, where are you? And it would ask if you're in the United States or if you're in another part of the world. And then it would look for a constellation that it was expecting. And if it found a different constellation, then it would reject your position. So I'm not really sure. They may have compensated for that automatically by this time, but that was 20 years ago or something like that. Just popped into my mind that that kind of happens once in a while. So the conclusion is that GPS was originally designed for military use at any time anywhere on the surface of the Earth, but that civilians may also use GPS for marine, car navigation, and also for surveying. So this is just sort of an overview of GPS. I think we'll do a little bit tighter lecture in the future, but in the meantime, if you would, engineering surveying students, please read chapter 15 of your textbook, and ES 2670, please read chapter 3 of your textbook. Bring any questions to me that you have, and we will continue our discussion of GPS with a homework assignment next week. So we'll see you, not today, Thursday, but we'll see you Tuesday in lab for sure, possibly in lecture as well for the engineering surveyors. But I'll let you know beforehand. Thanks.